today we will talk about rational versus Byzantine players in community-based blockchain. So it's a work we did with my advisors, so from CEA, inflict, and HEC. So just for a bit of context, so for the one who don't know about blockchain, I'll just give just you a description I want, but will not go that much into details. So we have a potentially unbounded number of processes in a system that discuss through message exchange. So they exchange message for whatever they want, and the goal is to build a distributed ledger. So every process should have a copy. The ledger should be temper resistant, so no one can forge or modify the content of the ledger, and we want it to be built in an append-only manner. So you can only add information at the end and not in the middle. And basically how blockchains do that is having a sequence of blocks. So there is the first block, the genesis one, and each block is linked to the previous by a hash. So the hash allows to have the temper resistance and also the append-only advantage. What we want is to have a chain structure, so at each point in time just having one block. So to avoid some problems, so we use the abstraction of consensus distributed systems, and basically the consensus is just those three properties we want. So at each time, we want to be able, we want to ensure that we will have a block coming at that height. That block should be the same for all the processes in the network, which is the agreement, and each block in the chain should satisfy a given predicate. So I don't know if it's a financial application we want, for instance, we should have valid transactions in the blocks. So how can we use consensus to build a blockchain? We have the first block that initializes the system. In that block, there is a first set of processes that is selected as the first committee. That committee generates a block through a consensus mechanism. So as I said before, once that block is produced, they broadcast the block to all the network. The network receives that block. A new committee is deterministically selected and known by everyone. That committee runs the consensus, produces a new block, and so on and so on. And once the block is produced, the committee that produced that block is rewarded with respect to conditions that are provided in the application. And there are some blockchains that exist that will exist that are doing that. So for example, tethering that we analyzed, which is basically the first that we were doing that, and hot stuff, which was proposed a few years ago, and which will be the core of the Libra financial application if you know about it. One thing that is really fun is the reward of the committees. Just one thing. If you have any question in the middle, you can ask. One thing that is pretty nice from blockchains is the reward. As I said before, once the block is produced, the committee that produces that block get the reward somehow. And the goal is having some, in a committee we can have correct and non-correct processes. Right? Once that block is produced, since we can have a block produced with a certain amount of correct, we want to reward only the correct one. Okay? So we need to somehow know who are the correct, who are not the correct, and do that. And that is one big problem with this kind of blockchains that did not exist before. And that is what we will try to study. The thing is, being in a committee and working has a cost, right? So for example, if I'm sending messages, I'm paying the cost of the sending of messages or checking something, I have to pay cost. And if I get a reward, it's a bonus for me, I would say. Right? So the thing is, we want to processes there can try to take advantage of that. They will try to minimize, for example, their cost and maximizing their reward. Okay? And we will go a bit into detail and technical stuff after, but that's it. Some of them can get rewarded, some of them can get punished, and the goal of each process individually is to increase its profit, basically. We'll go into that later. But just before that, I'll just give you the model I'm using here, and the question you want to answer. I presented you the consensus. So we'll take one instance of consensus. The question is, if we have rational participants that are just the ones that are trying to maximize a given profit, so minimizing the cost and maximizing the gain, can we still ensure the consensus? And under which condition? We have another set of processes. Processes and player are the same. From now on, I will use the term player because it's game theoretical terminology. The set is ordered. The size of the set is n, and everyone knows its order. Okay? That is a pretty hard assumption, but some protocols are doing that already. Messages are signed and signature cannot be forged. So once a player receives a message from another player, it knows who created that message. We have a synchronous communication, meaning that there is a bound, a known bound on the delay of the messages, and players are using that. And we assume also to the other assumption, messages cannot be lost. So at the end of a round, all of the messages are delivered. And asymmetric communication, which means that if one player receives a message at the end of the round, all the others also receive that message, which is also a strong assumption for the aim of this work. And we assume the bar model, which is basically Byzantine, altruistic, and rational, the first letters of those terms. Byzantines are the processes that can do whatever they want. Altruistic are the ones following what they are asked to. And rationals are the ones that are trying to maximize their profit. Here we will just use Byzantines and rational, and we will assume the worst case scenario from Byzantine. So we will not take any arbitrary behavior, but just the worst one. In this sense, I will give you a protocol now for just correct rational participants that should normally do the consensus. We have three phases. So the first one is the proposed. We have one person, so let's say the first one in the order, that will propose the block. The others, if when they receive, they will check if that block is valid with respect to the predicate, right? And then they will send a message, I vote for that block, if the block is valid. The others, when they receive it, they will count, basically, if there is enough vote messages for a block. If there is enough, then they will just accept. Otherwise, they will go back to the proposed phase where the next player will be the proposer. Okay? I'll just draw a bit like here on the scheme and to show you. As I said, we have phases. Propose vote, and if everything is correct, we'll just accept here. Right. We have four players. The first one is the first proposer. It will create a block, so let's say B, that is valid. It will propose it to the others. The others receive. They will check the validity. Since the block is valid, then they send a vote message. They all do that. And let's assume that we needed 3 messages for a block to be produced. Then the block is produced. And that's it. What we can do is...
Just a question for clarification for me. Is it the way it is done today with blockchains, or is it just a model and it is more or less like this?
It's a simplification of how blockchains work. For example, in Tendermint, the vote and the produce phase are a bit more complicated. But the core idea is that they check, and if it is valid, they send. And for example, we can, if we didn't want to stick with how the blockchain works, we could simplify this thing easily, since we assume that the messages are like all the messages are received at the end of the round. Once, like, we just let everyone send a message, right? And at the end, you just check the first one that is valid, and we just take that one. I mean, it can be as simple as that, but here we want it to stick, and then further to remove the assumptions to have a more realistic model. Right. So we have the block that is produced. And what we can do is to see that processes do have a cost. We can add the cost of the actions. So for example, we have all of them that checks the validity and they all send messages. So we can add that, and we have that. So CC is the cost of checking, CS is the cost of sending, and since the block is produced and they all send a message, we get the reward. Okay? So for now it's simple, that is what we want. So we can do decision tree for the processes and the actions they can take. Once the block is sent, they can either check or not the validity of the block. If they do check, they do have an information about the validity of the message. And then with respect to that validity information, they can decide to send or not. And whenever they send, they pay the cost. Whenever they check, they pay a cost. And you can see here, if we do not check, we do not have information, so we just decide about nothing. This is what we want the altruistic to do, but actually we do not care about that. But that is the protocol I showed you. So checking always the validity and sending only if it is valid. And what the Byzantine will do and what we studied in the worst case, as I said before, is to always check the validity because they do not care about cost, and not sending when block is valid and sending when it is not valid. Because of our assumptions, basically. If they send only if it is not valid, the thing they can do is making an invalid block accepted. But since everyone is receiving every messages, they cannot do anything worse. We will just use the notation new for the enough I said before. So the minimum number of messages we want to consider a block as produced, which will be new. We reward only the players that do send a message, because we cannot check if someone check a validity or not. So we just reward those that send a message at the end, and that is also basically how blockchains work today. Sorry. Yes.
Why don't you consider the two leaves at the bottom as Byzantine?
Here?
Yeah.
I mean, what I said by Byzantine behavior is the worst case. So when a player is Byzantine, it will do that as worst case. Because he doesn't care about cost, basically. So between does not check it and check, it prefers checking. Because it doesn't care about the cost, basically.
Okay, but he could send a random message even if he has no block to process. So you would be in the branch in the bottom?
If you did not receive a message, it's like you receive an invalid one. Since at the end of a round, you know that you didn't receive anything, so you consider it as invalid, basically.
Okay.
I don't know if you read that.
No, it's just surprising that you distinguish the case on your tree, and now you say me it's the same.
No, I didn't say that it's the same. What I'm saying is the Byzantine will do that. It is the worst case analysis. I mean, we did the analysis, and that is the worst case they can do. So we assume that they can do that. The others, so the rational, now, they have the choice. And the rational are not Byzantine, even if they behave as Byzantine. That will be clearer with the next slide. But if one decides not to check, it is still rational. It's not a Byzantine behavior, as we assume.
I have another question, because right now we assume for one round this is definitely the best behavior for the Byzantines, because they want to tell that basically they want the wrong outcome. But if we have several rounds, people will be able to remember, oh, I got validity check from that node, even though I checked and it was not valid. So they might game the system and say, yeah, let's pretend that now I follow the rules to be able later to.
We will use that. We will use that information in our solution.
Okay.
And also, so I think yes, we assume that there is a cost if an invalid block is produced. Just imagine you are on Bitcoin and you heard that there is an attack that was on Bitcoin. The value of Bitcoin decreases, so it's like a cost on everyone in the system, basically. That is what we were trying to model, and we call it kappa.
Also for the Byzantines?
They do not care about cost. I mean, there is a cost in their thing, but they do not care. Yeah. And we have this following assumption. The cost of invalid blocks is way higher than the cost of having a reward, that is higher than the cost of checking, than the cost of sending. I mean, it's kind of trivial. The only one that we can try to convince ourselves is just this one. Checking is more expensive than sending, but I mean, if you are on a computer, checking a mathematical function can be harder than just sending a message. So just show some example of execution now with rational players. So we have 4 players, they are all rational now. So for the moment, so let's say they are not rational. Okay? We can just see some kind of behavior that can happen, and then we will analyze the rational behavior. So the first one is the proposer proposes a valid block, it checks and send. The second checks and send also. The third, do not check, but that does send. I mean, why not? It's a choice. Before does check, but do not send. The block is still produced at the end, and we can see the outcome. You can see P4 doesn't have any reward because P4 doesn't send anything. That is what is important. In the second example, we have again 4 players. The first one is Byzantine now. So we'll send an invalid block, and we'll send only if the block is invalid. It will propose an invalid block, checks and send. The second checks and send, it was its choice. It's not the rational choice yet. P3 does not check but to send, and P4 does not check and send. We needed 3 messages for a block to be produced. The block is indeed produced. And we can see the cost. You can see all of them are paying the cost kappa, even though P4 doesn't send anything. That is the aim of this example. And the one that to get the reward are only the one that did send. So to study that, we use the concept of equilibrium that we call the perfect variation equilibrium, which is basically a subset of Nash equilibria. I mean, we have a Nash equilibria, so everyone is maximizing its actions relative to the others one. Are you all familiar with Nash equilibrium? Yes? Yes. And we assume another thing, that is the players in the system to learn, I would say, from the past actions. So what they see in the past are important in their behavior. Basically, that was your question. So that is what we will try to use, and they do those inference and those learning with respect to Bayes' law. And just to recall the question we wanted to answer or we wanted to study is it possible to ensure the consensus properties with respect to our model? So the presence of rational participants. We'll just focus on termination and validity, which are basically termination is we want a block to be produced at one point, and the validity is if a block produced should be valid. We do not care about agreement here for one reason, our model. I mean, our model implies agreement, so it's not that important here. For notation, again, N is the number of players in the set. Nu is the minimum number of required messages. F, that we assume strictly bigger than at least equal to 1, is the maximum number of Byzantine players. We assume that we have enough rational, so non-Byzantine players in the system to make a block produced. And the assumption I gave you. Okay? And we analyze a few different conditions. So first of all, we just assume that we do have a lot of Byzantine in the system. I mean, this one is just to see that the equilibrium is really what we expected is we have more than new Byzantine players. And we see, we analyze if there is, what can happen. I don't know if we have a situation, we needed new messages for a block to be accepted, we have new +1 Byzantine. What is the best behavior of the rational to do? Basically, they just send a message. They do not check, never, they just do send. In that situation, what happened is that at the first block, if the proposer is Byzantine, for example, the block that will be proposed will be invalid. Everyone sends a message for it, the block is accepted. And we have an invalid block accepted, that's why we cannot guarantee validity. If the proposer now is rational and proposes a valid block, all the rational also do send a message, right? Because in the equilibrium, they just send without checking. So we still have termination, even like at the first round, at the first proposition, but we cannot guarantee validity. And why is that the best behavior? Because if a rational is a proposer and proposes something valid, it's better to send anyway, right? Because in that case, you get a reward. If you did not send, you did not get anything. And it's finished. I mean, now, if we focus on the Byzantine as proposer, what can happen is they send the message. As we assume we have enough Byzantine for a block to be accepted anyway. So if whatever the rational do, basically, the block will be produced. Okay? That is the fact. So they will all pay the cost kappa anyway. So the best thing for the rationals is to try to minimize that cost by at least getting the reward R. Okay? Because the reward, you get it once a block is produced and you did send a message for it. Yes, this one. See here? You have a question? Yes, sir.
Just to be sure, we assume that we basically we have at least
we had more Byzantine than
yes, but also that the non-Byzantine adjuncts are enough to be able together to validate. Because, I mean, otherwise we know that we will validate if and only if.
Exactly. Okay. So you see here, for example, this P4 does not send. The block is produced anyway, and it was invalid. So this one is paying the cost without even sending anything. But if you see P3, for example, P3 does send, so does pay the cost of sending and is having a reward, and the cost of invalid block. We assume that RR is bigger than CS, so this value is positive. And then this thing is lower than that one, basically. So it's better, P3 is better off than P4.
Not only the next slide. Not only validity is not guaranteed, but it's for sure any block is produced is invalid, right?
No, because if the proposer is rational and that proposer sends a valid block,
the Byzantines will have interest on invalid.
the Byzantine will not send, because that is what they can do. They cannot do worse than that with our model. And since all the rationals are sending anyway, that block will be produced. Because there are enough to make a block produced by themselves. Okay? So this one is not that. It was just to be sure that even with rationals, we cannot break that assumption. I mean, it's obvious that the Byzantines are too much and they can break everything they want. So now we do the other one. We assume that we have a strictly lower number of Byzantine than the required value, and that implies that the new is at least equal to half. I didn't write here. We have that now. So we have at least half, at least n over 2 messages required for a block to be validated, and we know that we have strictly less than n over 2 Byzantine in the system. So what can happen? The first thing we see is that there is an equilibrium, so in the sense of perfect Bayesian equilibrium, that where no one, no rational, is sending anything, not checking. Why? Basically, if no one is sending anything, the block will never be produced. Anyway, if no one is sending. So if myself, I choose now to send something, that will not help at anything because we assume, because of this assumption, we have that nu is bigger than n over 2. So one person cannot change the outcome of an equilibrium, of the outcome, excuse me. Okay? So it's better to not do anything. So that one is an equilibrium that will always exist. Because we have what economists call equation failure, where everyone is expecting the others to do the work, and if none of them is doing it, it's better for any of them to not do it also. We have validity that holds, nothing is produced, so we do have validity, right? So that's it. And we can see another equilibrium that I will show you with an example. But just to give you, we have a new condition that appears, which is kappa should be big enough with respect to the cost. So the cost of sending and checking only. If you want to see how kappa should be higher, I can show you. But just assume that kappa is high enough to be a big cost. Right? And we have two kinds of players. As I said at the beginning, there is an index. All players know their order in a set. Right? And we use that. So there is a threshold. All the players before that threshold have a behavior. All the players after that threshold have a behavior. In our equilibrium, we have information such that once a proposer is rational, the block proposed is valid and then produced. Okay? So we have that fact that we are using. So what happened is that whenever we reach around f plus 1, that means that all the f first proposer were Byzantine. So the f plus 1 will be rational, then the block will be valid. And in that case, they will just all send the message without even checking. And I will show you that. Okay? We have something, and in that situation, we have both properties that hold. Okay, and let's just see how that behaves. Assume that we have, I don't know why I have this thing here. We have four players. We have P2 that is Byzantine, but let's see. P1 and P1, P2, and P4 are rational. What we say is that there is a threshold P3, min 3, such that all the players with index lower or equal than than 3 will check validity and send only if it is valid, basically. So those one will send only if it is valid. And this one will send every time, without even checking. For example, P1 is the proposer and sent. It checks. P2 is Byzantine, check the validity but does not send, as we assume. P3 checks and does send. P4 does not check but does send. The block is produced directly because we have the 3 messages we needed. And we can compute the cost. You can see that if any players, between 1, 3, and 4, does something different, profit will be lower. For example, if P3 does not send, it will not get the reward. The block will not even be produced. We'll go to the next one. But imagine now that P3 does not check. We can assume that it will just lose that situation because of this specific configuration. If we change that configuration now and ask P1 to be and have P1 as Byzantine, what we ask them to do is that they check, they see that it is not valid, so they did not send. P4 did send, the block is not produced, we go to round 2. And since we are in round 2, we know that there is only one Byzantine, they all do not check and just send. I don't know if you see what will happen if P3 here decided not to check. In here, it will have made an invalid block produced. The thing is that why we have that thing is we have the maximum number of players that can send a message without checking, such that all of them, they are doing already the best they can do. They just send. If we add that with the number of Byzantine, we have new minus 1 in the worst case. So whenever one of them change and send without checking, we will have new messages directly for any message, specifically invalid ones. And if we have invalid messages that are produced, then we are paying cost. That is the idea. So here we have a valid block that is produced also.
Yeah, just so when you have selected the identities to know which one will have which behavior, you assume we know F.
The maximum number, yeah. We have F that is known, yeah.
Okay. You have F or just an upper bound on F?
We work with the upper bound because if we want to have the thing is if we want to add a probability distribution on the number of players to know if they are Byzantine or not, the thing is first we need to know which kind of distribution we want to use, which I personally don't know. I asked my advisors and basically they also don't know. So we just stick with the worst case to see what can happen, and they can just work with that way. Okay. So everything is good, right? The question at the beginning were, do we have a good mechanism, a situation where we have the consensus property that holds? Yes. We had another one that was bad, but I mean it was plain bad basically. No one is doing anything. It's not that great. But the thing is, we did found another equilibrium, which is basically what we didn't want to have. Which is basically we have both termination that is that holds, so we guarantee termination, but validity cannot be violated. How? Imagine a situation where we have the same as before, right? We have just F strictly lower than n over 2 Byzantine. We have nu bigger than n over 2. So Byzantine cannot just do anything by themselves. But now assume that we have nu is such that we need all the rationals except one. So basically, no rational can change the outcome by itself. So we are 4, for example. We are 5, for example. There are two Byzantine, and we ask the number of messages to be 3. Is it enough? No. Again, excuse me. We have 6 total processes. We have 2 Byzantine, and we ask nu to be equal to yes 3. In that case, so we have 3. We want 3 messages to get access to for a block to get produced. We have 2 Byzantine, so that means there is one rational that can try to help, but can try to also take advantage and not doing anything. So the thing is, in that situation, what can happen is, imagine that all the processes, all the pairs, excuse me, do send a message without checking validity. Always. Imagine that everyone is doing that. So you as rational, what will you do? is, you know that everyone else is doing that, so the block will be produced anyway. So why checking if I can avoid that? The problem with that is if the block proposed is invalid, then that block will be produced, and then evaluate the validity property. Okay. We have a new condition, but that condition is not that strong. We just need one player in the system to not be that important, which happens in most of the cases, I would say. So yeah, we do have that thing. So just to terminate with the analysis, we did study something in a really strong environment. So our hypothesis assumptions are really strong for the moment. So we are trying to remove them little by little. We did find a good equilibrium, but first of all, we found that this equilibrium is not unique. So we have way more equilibria, and we found a bad one, which is really problematic, because what we have those two equilibria, which one to choose? Knowing that at the beginning of the system, the players may not know what the others will do. So let's see. And what we are trying to do now is to first extend the work to more environments, more settings, and removing the assumption from one by one. So that's it. Thank you. If you have any question, oops, sorry. Yeah, by the way, that is the assumption I was talking about. It is not that huge, basically, because we just have probability functions on the position of the Byzantine in the set, basically. So if the Byzantines are all in the first or at the end, that is basically those kind of probabilities, and we had these things that are basically less than half every time. So we are not asking the kappa to be that higher. Questions?
So this new is a system parameter, right?
Yes. Yes, exactly.
So this presence of the bad equilibrium can be prevented by just
Choosing the good new
to be more than n plus n plus 1.
No, there are some situations where we can have like the new equal f plus 2, where we can still have that case.
Depends on the order.
Yes, it depends on the value of n basically. And the biggest n is, the more choice we have for new, and then more opportunity we have to get in that case. But it's not that, I mean, we can still choose new such that for any n, if we, for example, we take new is equal to n minus f, we don't have the problem anymore. But it's a really strong assumption to ask always that much messages.
A question. So usually in distributed computing, we kind of assume that f is smaller than a third of the population, because there is this result that in most of the systems, if f is at least a third, you can make everything explode.
Yes.
So let's suppose we have this assumption. What would be the best new? Do you have some idea? You know that you have at most a third of n that is Byzantine. You don't know f.
I would say 2/3 of n, basically. Because yes, 2/3 of n should be enough. But the thing is, with our model, we are in a case where we need f to be less than n over 2. I mean, because of this assumption, yes, this one, the symmetric communication. If we remove that, and basically we did, and we just need some few things to correct before announcing the result, I would say. But if we remove that symmetric communication, we do have the f strictly lower than n over 3. It's because of our model that we didn't have it. But we do have that, and we have more problem to handle, basically.